Yes, so thanks everyone for being here. And yeah, as Brian said, it's really exciting to see how this field has grown subsequent to our first discovery of bulk quantum oscillations in the first unconventional insulator, samarium hexaboride. So yeah, I'm looking forward to new results at this workshop, and I think it will be a great discussion time. So I'm going to kick things off. I will talk mostly about samarium hexaboride, but I will talk a little bit more. Yeah, okay. That's the outline. So I'll talk about the discovery of quantum oscillations in samarium hexaboride, ruling out extrinsic contributions and how we can separate between gapped and gapless models. I'll then talk briefly about the rich quantum oscillation spectrum of multiple frequencies in the bulk unconventional insulator YbB₁₂, and talk about the hybridized Fermi surface that is seen in the field-induced metallic phase. And then I might put one slide up about our work in progress since then. So these are collaborators on SmB₆. As you can see, it's a large collaboration. Experiments were mostly done in NHMFL Tallahassee. There's several students and collaborators from Cambridge, and floating zone grown single crystals of SmB₆ were grown at the University of Warwick. And band structure calculations were done by Michelle Johannes. Okay, so as most of you likely know, samarium hexaboride, in this material, the gap opens because of hybridization between a flat F electron band that you see with red dashes here. And the green dash line is the conduction electron band. And so hybridization between these two opens up a direct and an indirect gap, and that's why the material is insulating. I'm also going to show specifically the band structure of SmB₆ calculated by Chang et al. And so the useful thing to look at is that this is actually a very simple conduction electron band structure. Yeah, so on the right, you can see it with the red dots. So the red dots are the unhybridized conduction band. They hybridize with the F electron seen in yellow. Sorry, that color is not great, but they hybridize with the flat F electron band seen in yellow to open up the gap and give you the hybridized bands seen in navy blue. And you can see the gap opening up there. And so this is quite important because, as you'll see, we find this conduction electron Fermi surface, which should not show up in an insulator, to actually, have a lot of relevance here. So it's really useful that this is such a simple band structure. And also for context, I'm going to start by mentioning that actually what kicked off this work was the suggestion by the group of Pierce Coleman et al. That samarium hexaboride is a bulk topological insulator. So the surface is conducting and the bulk is insulating was the suggestion. And so this is what motivated us to look for quantum oscillations, because before the nexus of this field, it would have been quite unthinkable. Like, why would you go look for quantum oscillations in an insulating material? As it turns out, this is actually not such a crazy idea, and there's many more materials now. But at that point in time, the reason we were doing this was because of the suggestion that maybe the surface is conducting, and maybe that would show quantum oscillations. So really importantly, all the results I'm going to be talking about here are on floating zone grown crystals of samarium hexaboride. So they're not grown out of any extraneous flux, no aluminum, nothing else. On the right, you see that triple R is very different between different samples grown in different ways, and different samples even within the same group that's grown samples. So what we needed to do was go and screen maybe about 100 or more samples to find those with the highest triple R. So any inclusions, metallic inclusions, would reduce triple R. So we only work with samples that have a triple R of at least 10 to the power 5. And you can see there's quite a big variation. So a lot of screening needs to be done to find samples which we then measure. I'm also going to give you the caveat that there is a lot of discussion about samples grown out of aluminium flux. And so these were grown by the group of Zach Fisk, and there was reports of 2D Fermi surfaces in these samples grown out of aluminium, and there's also reports that quantum oscillations can arise from the aluminium. I am only going to talk about samples grown by the floating zone methods, and that discussion about any effects of aluminium, I will leave to those groups to clarify. Okay, so you can see the resistivity goes up as one would expect for an insulator at low temperatures, plateaus maybe due to topological states, and importantly, at high fields of at least 45 Tesla, there's very little change in this resistivity. So even when we measured 45 Tesla, we're confident we're still measuring the insulating phase. And the activation gap we can fit, it's about 30 Kelvin or about 425 MeV. Okay, so to do quantum oscillation measurements, we use a combination of the 45 Tesla hybrid at Tallahassee, very pure single crystals, low temperatures down to dilution fridge temperatures, and torque magnetometry. So the first thing we did, because we were expecting oscillations from the surface, was to measure the resistivity, which is most sensitive to the surface, and we see nothing. So, you know, if we see nothing, it doesn't mean there's nothing there, but a null result could just mean the mobility is inadequate. So we measured a few samples, and then we just gave up saying, okay, the surface is not good enough. Even if there were oscillations, we're not seeing them. So then we measured the magnetic torque, and that was when there was a really big shock, was that we saw these very prominent, so this is not background subtracted, right? This is just the raw data. And we saw these very prominent quantum oscillations against a raw unsubtracted background. And the magnetic torque acts as the entire volume of the sample. So to see this large oscillatory signal on this background was very shocking, I should say. And we thought about several possibilities, and we measured several times. The sample fell in while we did all these, fell into the cryostat while we did all these tests. But it was multiple samples, and pulling it in and out, it was still there in our data. So then we started trying to understand this better. Okay, so we subtract out the background. On the left, you see oscillations of lower frequency going down to low fields. Also, I should clarify that we've measured several samples. The best samples show oscillations going down to 15 Tesla. The ones that are not as good, the oscillations only start above 25 or maybe 30 Tesla because they have more dingle damping. So this I'm showing one of the best samples we measured, which the oscillations go down to low fields. And at the very highest fields, you can see much higher frequencies onset. And that's quite important to ascertain, you know, electrons are undergoing large cyclotron orbits. So this is, again, a snapshot of the torque. So in this, you can see clearly all kinds of frequencies. Low frequencies are slow oscillations, ranging to high frequencies at the highest end. And you get frequencies ranging from 500 to 10,000 Tesla. And the largest frequencies are about half the Brouillon zone. So this is a significantly large Fermi surface. And again, you see a rich quantum oscillation frequency spectrum from a few hundred to tens of thousands of Tesla. So the first question is this a bulk Fermi surface? Given at that point in time, this was unthinkable that it could be from the bulk. So the first thing we do is to look at the absolute amplitude of the quantum oscillations to see whether this reflects the entire bulk of a sample or a tiny fraction. So we convert it into magnetic moment per bulk unit cell, assuming the whole sample is contributing. So the bulk unit cell we divide out by the entire volume. And if the whole sample were to contribute, we would get about 30 times 10 to the minus 4 Bohr magnetons per unit cell. We look at Lifshitz-Korsavich simulations and say this is assuming it's a metal, of course, but that's the best formula we have. So we just use Lifshitz-Korsavich and say what would we expect for the entire volume of the sample contributing, and it would be around a few times, 2 times 10 to the minus 3. So you can see that the size of the oscillations indicates that almost the entire bulk of the sample is contributing to these oscillations. Okay, so the next thing we do is we try to resolve the Fermi surface geometry. And here I have to state something that's really important if you haven't worked on this enough, is that you can't start with this multiplicity of oscillations and attempt to work backward and get a Fermi surface geometry. That's not wise, and it's not possible. The only way you can try to get from the frequencies to the Fermi surface is if you have some model, right? Some calculated Fermi surface that you're comparing with. So usually you have band structure calculations. Here it's an insulator. So we don't have band structure calculations, but instead we try to find analogies with other band structures, and I'll show you that in a moment. That's the only reason we even attempt to do this. So if we just had no model, it's not something that you should be trying to do. Okay, so on the left are frequencies of samarium hexaboride. You could see the angular dependence. And one of the interesting things we found is that the size of the frequencies and the angular dependence are very similar to that in lanthanum hexaboride, which is a conduction electron equivalent without any F electrons. And so this is not insulating. This is conducting. So it's metallic. You can look at the box on the right, where you can see that the resistivity in that case plummets as you go lower in temperature. So it's really curious that both the size of the oscillations up to around 10,000 or 15 kilotesla and down to 500 Tesla are very similar. And you can see there's minimal angular dependence, as you would expect for a three-dimensional Fermi surface. So then we explore this further, and together with our collaborator, Michelle Johannes, she simulates this unhybridized Fermi surface as the red dots you can see in this other calculation by starting with the insulating band structure and shifting it, right? You shift it to close the gap. And in that way, she gets a large Fermi surface equivalent to the unhybridized Fermi surface that would be seen in lanthanum hexaboride. You can see a similarity between these large pockets that, so I'm just going back, as you can see in the lanthanum hexaboride, that's the geometry that was expected. And that's what you would get if you close the gap in SmB₆. So now we can simulate the expectation for this large and little ellipsoidal pockets in SmB₆, and those are the black lines you see here. So you can see that actually we can get a great simulation for the samarium hexaboride if we start with this Fermi surface model of just the conduction electron unhybridized Fermi surface in samarium hexaboride, equivalently the lanthanum hexaboride. Okay, so the next question is, how can we possibly get a Fermi surface in an insulator? So just because all the experimental indications are that this is the case, we still need to ask ourselves, is there something other than, you know, the obvious Landau quantized oscillations? How can we possibly get this? So there were several suggestions that maybe quantum oscillations are arising from extrinsic impurities. And so we checked this very carefully. So one suggestion was maybe it arises from other rare earths like gadolinium, which are inclusions. And there was a suggestion by the group of Fermi et al. That when they deliberately put gadolinium in, you get a finite heat capacity, as you would expect, but it shows up in the magnetic susceptibility. So that's one way we can tell. So the thick pink line on here is what we measure in the samples that show quantum oscillations. So you can see the magnetic susceptibility basically shows almost no rare earth. So there's an upper bound of maybe 0.02, but you can see it's comparable with samples with no gadolinium in them or no rare earth inclusions in them. And it's also consistent with the linear heat capacity being consistent with the samples where no gadolinium is doped. So it's the lowest value of gamma you see there. So we can rule out that this is from extrinsic gadolinium. Also, NMR that our collaborator Leslie Mitrovich has done, you can see very sharp well-defined line shapes, which indicates high purity and no distribution of impurities. So the second thing is there was a lot of discussion about aluminum flux, and so I don't need to get into that. However, it is interesting to look at the fact that, so on the left, you can see that at the low frequencies, there is similarity between samarium hexaboride and aluminium. So it's interesting to probe this and to understand why this might be happening. So what we focus on is, so the low frequencies are similar, but when you go up to high frequencies, you can see that in the samarium hexaboride, we start seeing frequencies, a rich spectrum of frequencies, all the way up to 15 kilotesla, which are not expected in aluminium. Instead, in aluminium, you expect a large breakdown orbit of several tens of thousands, like 60,000 Tesla, which we don't see in the samarium hexaboride. So looking at the overall spectrum, then it's really clear that these are not correspondent to aluminium. It's interesting they're similar, but this may well be because the cubic lattice parameters are similar and the number of valence electrons are similar. You might expect similar size frequencies. But we rule out these oscillations from the aluminium, but also we make really certain, because if something so unexpected is happening, we have to check all the possibilities. So we do mass spectrometry on, this is a volume probe on the bulk material. So we look at the entire bowl from which we cut a sample to do our measurements. And to the limit of detection, there's no extraneous elements. This is a volume measurement, so it couldn't be missing anything. So this is inductively coupled plasma optical emission spectroscopy. And you can see that other than samarium and boron, there's no extraneous elements below the limit of detection, except sort of a few trivial elements around 100 ppm. So we've ruled out extrinsic impurities as a possible source of these oscillations. The next question is, do they need in-gap states to give these oscillations, or could it just arise from a gap system and the electrons are just tunneling across the gap, as been suggested by several groups? So they keep increasing the number of papers in this topic. So I'm just going to say that several papers have suggested the possibility of tunneling across the gap, including that of Knoll and Cooper. So our way of testing this is that the prediction of those papers, such as by Knoll and Cooper, is that as you go down to low temperatures, because the electrons can no longer tunnel across the gap, the quantum oscillation amplitude will either flatten or die to drop to zero at the lowest temperatures. So we look at our quantum oscillation amplitude, it clearly doesn't do that. It increases to low temperatures, actually anomalously, when you go down to dilution fridge temperatures. I don't have time to discuss that particular anomaly, but even down to 1 Kelvin, so on the right, is a 10,000 Tesla frequency. And you can see the strong increase as you go down to low temperatures. We also specifically blow it up at the lowest temperatures where we're most interested and do a low temperature expansion. So you can make x by sinh x to the lowest order in terms of polynomial, so it'll be roughly quadratic in the x term. And so we plot the lowest range of temperatures, the amplitude difference at the lowest range is a function of x squared, and you can see this conforms to what you would expect for Lifshitz-Korsovich, but importantly, the amplitude is increasing at low temperatures, which is inconsistent with gapped models. Also, we can get a density of states. So roughly, if we take the masses and calculate the density of states from the volume and the mass, you would expect gamma to be about 4. The measured electronic gamma, so again, we see this we see this rise at low temperatures. This is, I'm not going to talk about here, so I'm just going to talk about the low value of around 4 that it reaches at the lowest point before rising up. And interestingly, this upturn is similar to the upturn in the quantum oscillation amplitude. So that's like an even more complex phenomenon that happens, but at least down to around a few Kelvin, gamma is consistent with roughly what you would expect for the density of states. So this is consistent with an in-gap neutral low energy excitations. So yeah, to summarize this discovery in samarium hexaboride, we found for the first time that there is a bulk Fermi surface in the first of this bulk family of unconventional insulators. And interestingly, in this case, this is specific to samarium hexaboride, we find it mirrors the conduction electron Fermi surface. There will be more talks, panels, etc., talking about other experiments and theories about what the nature of these low energy excitations might be. So I won't get into that. I'm just going to summarize the findings from my experiment and how that can motivate trying to understand it more. I'm going to quickly talk about ytterbium boron 12 now. So this work was done, again, partly at NHMFL Tallahassee. Also, higher pulse fields was done at the Dresden High Magnetic Field Laboratory. Again, samples from Agita Balakrishnan's group at Warwick and Ukraine. Okay, so the most important thing to be said about YbB12 is that in this material, the band structure is much more complex because there are 2 bands hybridizing with the F electron band. So you can see here that you can see the parabola, the underlying parabola, again, like the conduction electron band in samarium hexaboride, but now there's 2 parabolas, one centered at W and one centered at X. So there's 2 conduction sp bands which are crossing the F electron band. So now we have a much more complicated band structure to grapple with, and this is going to make it more challenging to compare the observed oscillations with the band structure calculations. We observed multiple quantum oscillation frequencies, and unlike that in samarium hexaboride, the quantum oscillation frequency oscillations are seen both in magnetic torque and in electrical transport. But you can see the FFTs look quite similar, and the LK in this case, it's quite important to note that the mass that's measured here is a heavier mass. That's about 3 electron masses, which is much heavier than the SmB₆, which all the frequency masses were in the range of 1 or lower. So low frequencies had much lower than 1 electron mass. So this observation of multiple frequencies is not surprising, given that it's such a complex band structure. You would certainly expect multiple quantum oscillation frequencies. We look at the temperature dependence of the quantum oscillation amplitude. Again, we do the same thing we did before to test whether there are gapless states. And we can see the quantum oscillation amplitude rise down to low temperatures. And looking at the multiple frequencies, they all have heavy masses. So ranging from about 3 to about 8. On the left is magnetic torque, on the right is electrical transport. And you can see the similarity in masses for the similar frequencies observed in both. So then we try to do the same thing we did before, and we said, okay, let's look at unhybridized lutetium-boron-12 and see if there's a correspondence. Sadly, we don't have the same nice comparison we can make in this case. So we went and measured single crystals of lutetium-boron-12 to make this comparison. Again, band structure that Michelle has calculated. You can see the prediction is for large Fermi surfaces with light masses. So we measure lutetium-boron-12, the effective mass is about 0.5. So this is characteristic of a large conduction electron Fermi surface, looks nothing like what we see in the YbB₁. We also measure quantum oscillations in the field-induced metallic state. So YbB₁ is different from samarium hexaboride in that we can access the field-tuned metallic state. So this is proximity detection oscillator method. So you can see the resonant frequency suddenly change when the material metallizes. So above 47 Tesla, there's a sudden change in the frequency, and you can see oscillations superimposed again on the raw background. On the right are oscillations extracted at many temperatures between 0.6 to 2 Kelvin. Again, you can see here a very complex frequency spectrum. There's not just one frequency, there's multiple frequencies. And also really importantly, we can simulate this entire spectrum by combining 6 frequencies with the Lifshitz-Kossovich 1/b simulation. We can simulate this entire spectrum with the frequencies we see in the FFT that I will show you in just a moment. So this again looks very much like basically a multi-component frequency spectrum with oscillations that look 1/v, and here Lifshitz-Kossovich like. So on the left-hand side, you look at the FFT, so you can see multiple frequencies and the change in temperature. On the right is LK, and you can see that we get very heavy masses up to about 17 electron masses. So again, what's important is that there's no sign that this is becoming unhybridized. One might have expected that at high magnetic fields, we've unhybridized the Fermi surface and we see the conduction electron Fermi surface. No, actually what's happening is that the low frequencies are very similar to that seen on the insulating side. The masses are similar, but we also start seeing large sheets which are much heavier. So we are seeing the onset of more large hybridized Fermi surface sheets. So this is a comparison between insulating and metallic. You can see the low frequencies are in a similar range with similar moderately heavy masses up to 9 electron masses below 1,000 Tesla. But above that, in the metallic phase, you start seeing many higher frequencies up to 3,000 Tesla and a mass of up to 17 electron masses. So yeah, this is not consistent with a light conduction electron Fermi surface. What it is consistent with is earlier heat capacity measurements by Terashima et al., which show a sudden increase in the value of gamma as you cross the metallization, which would be consistent with these new large, heavy Fermi surface sheets onsetting beyond the metallization transition. What is still an open question, because we don't have a nice Fermi surface model to compare it to, what is still an open question is what is the Fermi surface model that can explain this multi-component heavy hybridized Fermi surface on both sides, the unconventional insulating and the field-induced metallic YbB₁. So one of the things that we have found is that, in both of these cases, we seem to be contravening our expectation that you only see Fermi surfaces in a metal. But it seems like once that has broken and you are now in, out in sort of the Wild West, where you see different Fermi surfaces, different quantum oscillations that appear to sort of break this metal Fermi surface correspondence in different ways, which is really interesting. And I think it really points to looking at more materials to try to understand all the possible ways in which it can break down in more of this family of unconventional insulators. And I'm just going to very quickly show a third material which we're working on, which we also see quantum oscillations. It's an insulator, but again, I won't go into details, but again, they're different from what we see in the previous cases. So yeah, this is just to show you 1/B quantum oscillations in another material. And looking at all of this, I think one of the things we can say is that the more unconventional insulators we look at, the more ways, it seems like the more interesting and inventive ways can one have a breakdown of this sort of tenet we assumed was true, that a Fermi surface can only occur in a metal. And yeah, it's really exciting to see how far the field has come. And I think that prospects are really good for seeing even more materials and possibilities from theory to, think of creative ways in how this can happen. Thank you.
Okay, thank you very much, Suchitra. Aurel, we have a considerable amount of time for questions, almost 15 minutes. So if you have questions, please use the hand raise feature, and I will call on you to unmute yourself. You guys know what the hand raise feature is down. I think if you click on the reaction button at the bottom of your screen, you'll find a hand raise thing. Okay, I see Colin Brohon. Colin, if you can unmute yourself, please go ahead and ask your question.
Yeah, beautiful talk. And I noticed that very deliberately you say that you've seen the Fermi surface and that there is a Fermi surface. And I just wanted to understand the reasoning that lies behind that, because what you do see kind of directly is a quantum oscillation.
That's a very good question. Of course, this is not an immediate assumption. So the reason I say we see a Fermi surface from our own measurements, so I think what I briefly showed, so yes, this is the difference between gapped and gapless, and I completely agree that this is an important distinction to make. So just from quantum oscillations, it could come from a gapless model, which would not imply a Fermi surface. So from our measurements, from the fact that the quantum oscillation amplitude keeps increasing down to the lowest temperatures, down to millikelvin temperature, so this is much smaller than the gap energy size. That's one of the indications we use from our own measurements. From complementary measurements, for instance, there is heat capacity, which is not in and of itself conclusive, given that, of course, one could have an impurity contribution. However, there is a finite linear specific heat term, so there's that evidence. I haven't shown it here, but there are NMR measurements of a finite 1/T1T, which again are consistent with states in the gap. So yeah, I agree that just the observation of quantum oscillations doesn't translate into the observation of a Fermi surface, but I think that there are complementary measurements and analyses that we can do from which we conclude that it's consistent with these oscillations arising from in-gap low energy excitations and not from the gapped model.
Okay, thank you. I hope you don't mind if I jump the line a little bit and ask my own question here. At some point, you commented on the temperature dependence and how that seems to rule out scenarios like the one proposed by Knolle and Cooper, where you sort of tunnel across the gap. But my understanding of their mechanism is that it gives you well-defined oscillations even at zero temperature, and that it's not a thermal activation, but something associated with a kink in the band structure itself.
Yeah, it's not just a thermal activation, but they actually simulate the quantum oscillation amplitude and it drops to zero at zero temperatures. I'm taking this directly from their simulation.
I see. Okay. Well, if either Johannes or Nigel is around and wants to correct my understanding, then go ahead.
Just a short comment to that. So for the magnetization, it actually doesn't drop to 0. So it's always finite. It's only if you would measure like Fermi surface properties, like things which would be activated Arrhenius type. But the magnetization itself is finite.
Right, but it either flattens or drops, right? Would it keep increasing? Because I don't think there's any models it would keep increasing.
Well, not so. You of course, in our system, you can basically just let it touch one of the bands, and then you would get something like with a steep increase when you reach a temperature scale, seeing that. But it's true that you're right. If we are really insulating, then ours would just be finite, but it wouldn't actually have this big increase. But yeah.
Yeah, so if it were to touch a band, you would see conduction, and as I showed you earlier, there's no conduction. So I do think it's inconsistent.
Okay, thanks. Let me move on to the next question. Patrick Lee, if you're here, go ahead and unmute yourself.
Yeah, I just for clarification. So in the case of the terbium, so in the low field, you have an insulating regime, and do you see Schumacher-Has in that case, or no?
Yes, the FT is on the right. Sorry, I don't have a pointer for some reason, but yes, we do see on the right is transport. I don't have the oscillations up on my screen, but yes, the FFT on the right is from electrical transport. Yes, we see it in both.
So the resistivity is very large at low temperatures, it's mega ohm?
The resistivity, yes, the resistivity itself is very large. It is several ohms, yes, in the resistivity. So you see it against a background that is insulated. It is not as high, yes, there is a caveat. The electrical resistivity is not as high as in the samarium hexaboride. So yes, it is not as strongly insulating as the samarium hexaboride. That is correct.
I see, but is it exponentially rising, or is it?
Yes, it is exponentially rising. Yes.
But it is rising.
Yes.
So what happens if you keep going to lowest temperature?
I don't think I've shown it here, but you mean the resistivity or the quantum oscillations?
Resistivity first, yeah.
The resistivity, the plateau is not as obvious as the samarium hexaboride. It does turn over, but it just reduces in slope. It doesn't flatten.
I see. And the fraction of the oscillation is how much?
The oscillations, our oscillations are fairly a small percentage, so they would be a few percentage.
Oh, that's substantial. I guess a related question is back to samarium hexaboride.
Yeah.
So there is a finite gamma, specific heat gamma.
Yeah.
How does that relate to your mass of 1? Is it consistent with a mass of 1?
Yeah. So yes, so that's what I showed here, right? So we take a mass of 1 and calculate, you would get a gamma of about 4. And that's consistent with the lowest gamma you see here. There are complications, right? So if I were to take, so the 1 I take is from down to 1 Kelvin. And I'm not quite sure how to treat this huge increase below that. But if I take down to 1 Kelvin in both quantum oscillation amplitude and heat capacity, then they're both consistent.
Okay, thank you.
Okay, thanks, Patrick. I think Senthil had his hand up next.
Yeah, so thanks, Suchitra. So I want to understand the terbium boron 12 data that you showed. Maybe I got this wrong, but it seemed like you were reporting sort of similar frequencies in both the magnetization and resistivity.
That's correct, yes. So it's right here.
So that is different from what I recall from Luli and Matsuda. So is it a sample difference, or do you ever see differences?
Right, so this is actually why I specifically mentioned that the band structure is much more complicated, right? So that group reported only one frequency. And I think that you are certainly going to have multiple frequencies. I don't think there's any question in such a system, which the band structure is, there's electron and hole pockets, and there's 2 sets of conduction electron bands. It's actually not even possible. And the Fermi surfaces are not at gamma, they're away from gamma. So if you look at this, so it's actually impossible. You would get only one Fermi surface, you would or quantum oscillations corresponding to one section, you would certainly have more. I think I think that, even differences in, say, sample geometry or small strains or whatever could emphasize one of the frequencies over the other. But I think both of us see quantum oscillation frequencies that are low and heavy. So we see below 1,000, we see about 3 frequencies below 1,000 with masses up to 9. They strongly claim they see only one. I think the seeing only one just means one is dominating over the others. I don't think it's possible one can see a lone frequency and no other frequencies. So I think we're both seeing characteristics of a multiple Fermi surface characterized quantum oscillation spectrum. But and we see similar properties, but very small differences can just cause one frequency to dominate more than another.
Hey, Brian, can I comment on that? Since
yeah, go ahead and make a brief comment.
Yeah, this is Lou. I'm sorry, I'm in office. Let me take my okay. All right. Yes. So I agree with Suchitra, right? The Fermi surfaces are going to be complicated. The first effort will be bringing the most dominating feature coming out and try to find out what's going on, similar or different. I think the major difference we are observing between SDH and dHVA, frequency-wise, is pretty close, given both groups observe at the most 3 wiggles. The difference about 100 Tesla out of 700, 800 Tesla, I would call it's within the range. It's the same frequency, right? The only difference between our data and Suchitra's data, beautiful data by the way, the mass is different. If I remember the table right, in her data, the same pocket gave more or less same mass, about 8 or 7 ME. Whereas in our data, I'm going to show that in the dHVA it's 8, but in SDH it's about 14. So what's going on? How to think about that? It's an open question. I'm just trying to give an aspect from the data. Thanks.
Yeah, I agree with Lou. I think I would, his assessment agrees with mine, that I think both of us are seeing frequencies in the hundreds with heavy masses, and this is clearly different from a large conduction electron Fermi surface. And so I think that the differences are smaller than the similarities.
Okay, thank you.
Yes, thank you. All right, next question. We probably only have time for one or more, so I'm sorry for you guys who are later in line, but I think Bhaskaran was next.
Suchitra, very nice talk. So I have a short question. In samarium hexaboride, pressure also materializes a system. And also there is indication of magnetic order. So in ytterbium system, when you apply magnetic field and metallize it, is there an indication of magnetic order, recovery of RKKY kind of order?
Yeah, that is a very good question. There's no strong evidence for that as far as I can tell. Yes, that's as much as I can say. We don't see any sudden change in magnetic properties, at least at a very substantial level is the most I can say about it. I don't know if one can say whether there's sort of subtle changes in sort of low moment magnetization that develops or fluctuating magnetism that develops. All I can say is we don't see a large moment suddenly develop.
Thank you.
Okay, one last question from Chandra Varma, please.
Hi, Suchitra, to your amazing specific heat result. Can we see that again, where there is a singularity at low temperatures or apparent singularity in samarium hexaboride?
Yeah.
I mean, this is extraordinary. Does something else happen at that temperature?
This is a really good question. No, so from transport, nothing happens. So transport, you can keep going down to like millikelvin, and not our group, but a group in TIFR actually went down to like microkelvin. Nothing happens. So clearly something is happening because the oscillations also show this increase below 1 Kelvin, and heat capacity also shows this, but it must maybe the nature of the excitations or maybe a hidden transition. I don't know more than
I cannot tell what temperature this is occurring. This is at 1/10 of a Kelvin.
Oh, you mean down? Oh, it's below about 500 millikelvin.
Do you have oscillations across that temperature?
Yes, we do, and nothing. Oh, sorry. Yes, so oscillations. So the oscillation amplitude is what changes, right? So below 1 Kelvin, on my screen now, on the left, we went down to dilution fridge temperatures, and this is on a log scale, so it's artificially zooming that. But yeah, the oscillation amplitude does dramatically increase at low temperatures.
But C over T does not follow this. If you plot it on the same scale, will it look something like this rather than vertical?
I wouldn't say it's exactly the same. I would just say that qualitatively the features are the same. They're not precisely the same.
Anything happen at NMR or μSR in that temperature?
Yes, so NMR shows a finite value. However, they only value 1 over T1T, but they can only measure at low temperatures unambiguously. So almost all the measurements are below 1 Kelvin. So yeah, I guess we're always in that range there. So I can't tell whether there's a sudden change.
I might just add, we see a striking change in behavior in NMR below 1 Kelvin. Something happens below 1 Kelvin. It's very different than at high temperatures. So,
what happens?
Behavior completely, it starts looking like a metal, actually. Yeah.
Meaning it becomes, relaxation rate becomes linear in T?